You know all those green technologies we're banking on for our future? Things like electric cars and massive wind turbines. Well, they all rely on this incredible family of materials called rare earth elements. But here's the thing, their name is kind of misleading. They're absolutely key to a cleaner world, but they come with a hidden cost, a cost that has created a massive global dilemma.
So, you look at these three things, right? An EV, a wind turbine, and a fighter jet. They seem like they have absolutely nothing in common. One's for clean transport, another for renewable energy, and the last one for national defense. But they all share the exact same critical dependency.
Well, the secret ingredient they all share is this family of 17 elements called rare earths. Now, they aren't exactly household names like iron or aluminum, but their unique magnetic and electronic properties, they make them completely essential for pretty much every piece of high technology we use today.
But here's the catch. Getting these elements out of the ground and into our devices, well, that is a story packed with incredible technical hurdles, major environmental trade-offs, and some really intense geopolitical maneuvering. And that's the story we're going to unpack.
Okay, so to really get our heads around this whole complex issue, let's zoom in and focus on just one of these 17 elements. Let me introduce you to dysprosium. It's a perfect example of both the amazing power and the huge problem of rare earths.
All right, so this is dysprosium. It's what's known as a heavy rare earth, and its superpower, it really is a superpower, is making the world's strongest magnets even stronger. See, if you add just a little bit of this stuff to a magnet, you make it way more resistant to losing its magnetic charge, especially when things get hot. And in any high-performance motor, whether it's in an EV or a wind turbine, heat is the ultimate enemy. Without dysprosium, those motors would just fail. Simple as that.
And believe me, that superpower is in high demand. We're talking about the motors in electric vehicles, which need dysprosium to handle all that stress. It's in the generators of those giant offshore wind turbines, helping them churn out power reliably for years and years. But it doesn't stop there. It's also critical for defense systems, for the hard disks that store our data, and even in the control rods that keep nuclear reactors safe. So think about that for a second. This one element underpins green energy, big data, and national security.
Okay, so if this stuff is so important, why don't we just, dig up more of it? Well, this is where the real problem starts, and it begins with that word rare. See, the name rare earth is actually a bit of a misnomer. They're not really that rare in the Earth's crust. One of them, cerium, is actually more common than copper. The real problem, the thing that makes them so expensive and difficult, is that they all kind of look and act the same chemically. They're all found clumped together in the same ore, and separating them is a nightmare. And you know what? The name itself is a dead giveaway. The scientist who discovered dysprosium back in 1886 named it after the Greek word dysprositos, and it literally means hard to get. How perfect is that? He called it that because it took him more than 30 tries just to get a pure sample. The name was basically a warning label. So this gives you a rough idea of the brutal process it takes to get that pure dysprosium. After you mine the ore, you have to crack it open with some seriously strong acids. But then comes the really hard part, the separation. Because they all behave so similarly, this involves a process that has to be repeated hundreds, sometimes thousands of times, just to slowly, painstakingly tease one element away from the others. It's a brutal, chemical-heavy process, and that has some major consequences.
So because this process is so difficult and, frankly, so dirty, not many countries wanted anything to do with it for a long time. And that created a huge opening for one country to step in, invest strategically, and basically become the world's only refinery.
And that country, as you probably guessed, is China. While the actual mining happens in a few more places these days, that absolutely critical separation step is almost completely dominated by China. We're talking over 90% of global processing. What this means is we have a massive geopolitical choke point. And look, this isn't just some what-if scenario. It has already happened. Back in 2011, China decided to restrict its exports, and the result? Dysprosium prices went through the roof. I mean, this shot up by more than 9,000%. It was a huge wake-up call for everyone, showing just how vulnerable the world's high-tech supply chains really are. And just to add another layer of complexity, the very best and easiest sources for heavy rare earths, like dysprosium, are found in these special deposits called ion adsorption clays. And where do you think most of those are? Yep, southern China. So the geology itself kind of locks in this dependency.
So obviously, this situation set off alarm bells everywhere.
And now there's a frantic global race to build new, independent, and more secure supply chains for these materials. Everyone is scrambling.
The game plan for breaking this monopoly has a few key parts. First, you've got to diversify, open new mines in new places. Then, forge alliances, what people are calling friendshoring, basically working with your allies. You also have to innovate, to find cleaner ways to do this messy processing. And this is a big one, we've got to build a circular economy and get way better at recycling these precious elements from all the old electronics we throw away.
And this is really happening right now. It's not just talk. In the US, you've got the Mountain Pass mine in California roaring back to life, trying to build a whole supply chain, from the mine to the magnet. Over in Australia, a project called Browns Range is aiming to be the first big dysprosium producer outside of China. Then you've got these alliances forming, like a new agreement between the US and Argentina. And in the UK, they're getting serious about recycling, building plants to pull magnets out of old hard drives and speakers.
But let's just say we fix the geopolitical problem. Even then, we are left with a really deep and uncomfortable question: the actual environmental price tag of making these supposedly green materials.
And this is what some people call the green paradox. On one hand, you have the promise, the dream, zero-emission cars, clean wind energy, a sustainable future. But on the other side, the reality, the dirty secret behind it all, is radioactive waste, chemical-filled wastewater, and even the risk of mining in really fragile ecosystems.
The reason for this is that rare earth ores are often mixed up with naturally radioactive stuff like thorium and uranium. And that intense chemical process we talked about, well, it concentrates all those hazardous materials into a toxic sludge. It's a tough pill to swallow, but the path to a clean energy future runs right through some pretty messy industrial zones.
So, where does that leave us? After all this, the insane chemistry, the geopolitics, the environmental mess, is there an easy button? Is there some simple, elegant way out of this dilemma?
Yeah, you probably guessed it. The answer is a hard no. There is no magic fix here. The only way forward is going to be complicated and challenging. It's going to take a mix of things. Yes, probably some new mining, but done way more responsibly. We absolutely have to get much, much better at recycling. And we need some big brains in the labs to come up with better, cleaner processes. And maybe, just maybe, new materials that can do the same job without rare earths at all.
Honestly, figuring this out, how to get these materials in a way that's both secure and sustainable, it is one of the biggest and quietest challenges of our century. The success of our entire shift to green energy really depends on us getting this right.
And so it all boils down to this one final tricky question. We know we need these materials to build a greener world, but can the road to a cleaner planet ever be truly clean itself? That is the dilemma we all have to face.